Hi, everybody. We are back to continue our discussion of hypothesis testing. In the last segment, we took a look at just some logic with thinking about the types of errors that we could run into in the decision-making process in the context of hypothesis testing, namely type 1 and type 2 errors. And we summarized the approach we're going to take here in this diagram where given some acceptable level of type 1 error alpha, which is known as the significance level of our test, that alpha in each of these three cases of a lower-tailed test, an upper-tailed test, and a two-tailed test will define for us what is known as the critical z-value that'll separate the rejection region from the non-rejection region. And again, this is in all three of these cases, we have some set of critical values which tell us how far enough away we would need to be from the null hypothesized value of the mean in order to say that our sample mean invalidates our null hypothesis, and we would reject it in favor of the alternative. So we're going to go through a few examples of this process. First, we're going to start off with just thinking about identifying this critical value threshold. And the way we're going to do that is related to something we had done on a previous video, which was kind of using the process backwards. Instead of starting with X, converting to Z and getting the probability, we're going to start with this acceptable probability alpha, our type 1 error. We're going to figure out what is the Z threshold that corresponds to that alpha, and then we can convert that back to an X value to see whether or not our sample data falls to the left or to the right in that reject region or the do not reject region in terms of our null hypothesis. So first question we're going to look at here is thinking about determining the critical value for a 5% upper-tailed test. Okay, so we're given here an alpha value of 5%, which means if we're looking at our distribution and it tells us we're dealing with an upper-tailed test here. So the question is, what is that Z value that's going to leave exactly 5% probability in that upper tail? Now remember, we're going to use our standard normal table to help us figure this out. And the standard normal table does not give us that upper tail probability, but it does give us the probability in this region between 0 and Z, which we can easily calculate here has to be 0.45. We take 1/2 minus that 5% upper tail. That leaves us with the probability of 0.5. And then we can go ahead and take a look at our one-sided standard normal table here. And we can go ahead and look. And if you notice around this row 1.6, the value 0.45 isn't exactly there, but we have these two values that are on either side of 0.45 equally. They're 0.0005 above and below that value respectively. And if you look up at the columns here, you'll see it corresponds to either a value of 1.64 or 1.65. So we're going to go ahead here and just kind of average those two values to compute what that Z threshold is. And that comes out to a value of 1.645 as approximated by that standard normal table. So if we saw a Z value in our data that was farther away, like I got a sample mean X bar, I convert that to Z, and it's farther away than 1.645 standard deviations to the right, then we could say, hey, that's far enough away where we can reject the null hypothesis. How far is far? This is telling us here under the critical value approach that 1.645 standard deviations to the right of the mean is sufficiently far away to reject that null hypothesis. So let's go ahead and take a look at another example here. Now the question says, let's determine the critical values for a alpha level of 2.5% for a lower tailed test. So again, I think it's useful always to draw the diagram here. We're now allowing ourselves to have 0.025% probability left in that lower tail. And again, the question is, what is that Z value threshold? And we can again compute the area in between 0 and that Z value in this region here, which is 0.4750. And that is the probability now we need to look up in our standard normal table. So again, if we jump back to that table, I'm looking for a probability of 0.4750 in that table. And you'll notice That probability, we can find that 0.4750. That is right here. Okay. You can see that probability is exactly right there. So that corresponds to a z-value of 1.9. And then we go to this upper column here, and we can see that that is a 0.06, implying that our critical value threshold in our problem should be equal to this value 1.96, but since we're to the left side of the mean, again, it's got to be negative. Remember that one-sided standard normal table only gives us the probabilities in terms of the absolute z-values. So correct answer here is going to be choice D. Let's go ahead and do one more example of figuring out what the critical value threshold would correspond to for a particular level of significance in a test. So next problem, here we're now going to determine the critical value for a 5% two-tailed test. Now remember, if you have a two-tailed test, you're going to have to take that, that significance level and you're going to have to split it in half, because we're going to allow some probability in either tail, right? The two-tailed test, we're allowing ourselves to say how far away is far enough, not in one direction, but in both directions. Okay, so in order to do this, again, we're going to need to compute our table values here. And you'll notice we can use just 1/2 of this picture. I need this area here. And we can get that area by either taking 1 minus 5% and dividing that in half, or we could take 1/2 and subtract 0.025 to figure that out. And that'll give us a value of 0.4750. And I think that's a familiar value because we saw it in the last example here. So I'm not going to jump back to my standard normal table. We know 0.4750 corresponds to a z-value of 1.96 in magnitude, which means the threshold in terms of the number of standard deviations away from a z-value of 0, we would need to be in either the right direction or the left direction, has to correspond to plus or minus 1.96, which is going to correspond to choice B here. Okay, so those were 3 examples of how to figure out the critical value. So the critical value, that's what's going to define the threshold for our test of how far enough away we would need to observe a sample mean to say that our assumption about the population mean is probably not reasonable under the null hypothesis, and we can go ahead and reject that in favor of the alternative. So again, the critical value approach, let's go ahead and just kind of summarize the logic here. The way we're going to do this is we're going to convert our sample statistic to a test statistic, which means we're going to take our sample mean and we're going to convert it to a z-score or a t-statistic. We'll get to that in the next segment. And then we're going to go ahead and determine the critical values for a specified user-chosen level of significance alpha. So that's what we had just done, actually. We had just completed the second bullet point here. And then we're going to figure out the decision rule. Okay, whether or not we should be rejecting in a particular region or accepting or not rejecting the null hypothesis in a particular region. So again, if that test statistic falls in the rejection region, if our sample mean falls far enough away, we're going to reject that null hypothesis. Otherwise, we will not have strong enough evidence to reject that null hypothesis. And just like our confidence interval case, we're going to start out in a situation where we know what the population standard deviation is here to start. We'll relax that assumption in the next segment, jump back and use the t-table to help us a little bit. But again, that hypothesis population mean mu, that is the status quo benchmark that we are testing. The value of mu is not coming from a sample here. The test statistic does come from a sample. So the test statistic, we're going to essentially compare X bar to our hypothesized mu and check how far is X bar away from that. If it's sufficiently far away, we can say, hey, mu is probably not correct here. It's probably not where we had hypothesized where it is. And the way we're going to generate that test statistic is pretty is familiar to us. We're just going to compute the z-score by utilizing the standard error as the standard deviation that we're dividing by in the denominator of that expression here. Okay, so if we didn't know sigma, we would just replace sigma with S here. This would turn into a t. We would use that t table instead, but we're going to come back to that. Now, we had discussed an example problem not too long ago where we were recalling a situation where we're planning on bringing a new product to market, and the plan would only succeed if the cost of production was lower than $10 per unit. We're going to assume sigma is known in this case to just run through this example. And again, we got to specify the population parameter of interest here. And what we're interested in is the mean cost of production. Okay, and the next thing we need to do is state the appropriate null and alternative hypotheses. So the null hypotheses here, again, is what we're trying to essentially disprove. So we're going to say, hey, let's assume the status quo is that the cost of production is $10 or higher, which is no good for us. What we want to be able to show with our data is that the cost is sufficiently low. So remember, what you're trying to show with the data typically conforms with the alternative hypothesis here. So we're going to be looking for evidence that the sample mean is very, very low, right? The null hypothesis is that the population mean is high, greater than or equal to 10. But we're going to look for evidence against that the sample mean is sufficiently low, okay, which means maybe if we can find that to be the case, the alternative is a more reasonable hypothesis than the null. So since we're looking for a very low sample mean, this is a lower tailed test that we're going to be conducting here because we want to prove that the mean is less than 10. Okay, so we're assuming the opposite of what we want to prove, and we're going to try again this idea of proof by contradiction. Okay, note the alternative hypothesis has that strict inequality, and now we're in a position to consider the decision rule given a particular level of alpha. So we're going to go ahead and use a 5% level of significance for this problem. I would always recommend, again, drawing this diagram. So we're leaving 5% probability in that lower tail, which means if the sample statistic, the sample mean after we convert it to a z-score, falls in that left region into that lower tail, that tells us we're far enough away from the middle here, right? We're far enough away to the left where we would have a statistically significant result that is different than the mean. It's far enough away where we would be able to reject the null hypothesis. So again, since we know sigma, we're going to assume we know sigma in this case, the cutoff value is going to be determined by a z-value. And in order to find that z-value, we need to know that interior probability in this region here, which is 0.45. We take 0.5 minus 0.05, and now we can go ahead and figure out the critical value. Recall we already saw this particular example here where we had to look and we noticed 0.45 wasn't exactly in our table, but it was in between these two values, 1.64 and 1.65. So we averaged those out, and this gave us a critical value z threshold equal to negative 1.645 in the case of a left-sided test. So that is our critical value. If we observe a sample statistic x bar, we convert it to z, and that sample statistic after we convert it is smaller, farther to the left than negative 1.645. We will fall in this reject region, and we'll be able to say we can reject the claim that the production costs were $10 or greater in favor of the alternative that says statistically we have evidence that shows our product cost is actually lower than $10 here. So again, the decision rule is to reject that null hypothesis if the test z-value is smaller than our critical value. Otherwise, we're not going to be able to reject that null hypothesis because we don't have convincing enough evidence here in terms of extreme enough evidence. So the next step in the process, we're going to go ahead and obtain the sample evidence and compute the test statistic. So let's suppose here, off the assembly line, we randomly select 40 product runs, and these yield to us an average cost of $9. And you're like, oh, great, $9 is lower than 10. Yes, but remember, that $9 sample statistic is a function of the exact 40 production runs that we had sampled. If we sampled a different set of 40 runs, we may get a different sample mean. So there's a little bit of sampling error, some noise there that we have to be careful of, which is why we're accommodating for that uncertainty when we run this hypothesis test. So here are the parameters we're given. We have a mean of 9, a sigma of 1, we have a sample size of 40, the hypothesized population mean that defines our threshold is 10, and our alpha level is 5%. So we're going to use this information now to compute the test statistic. Okay, so we can go ahead, plug these values in here, and compute the z-score for the test statistic, which comes out to minus 6.32. Okay, and notice minus 6.32. That's over 6 standard deviations to the left of the mean. That's an extreme value right there. Okay, very extreme value. So at this point, we're going to take that test statistic, we're going to come back, we're going to compare it to our rejection region and our do not reject region. And we can see here that test statistic is way smaller than the z-value. So the conclusion here in running this test is that because our test statistic falls in that rejection region, it is smaller than the critical value of negative 1.645. We can reject the null hypothesis that the mean cost of production is greater than or equal to $10. So that is the core logic that we're going to apply. Let's go ahead and work through one more example, just a series of examples, and then we will end this video and we'll jump in the next segment to dealing with this if we have to actually estimate that population standard deviation, that sigma value with S, our sample standard deviation, and use the T statistic instead. So let's go ahead here and take a look at another case study situation. So to get a loan, a clothing retailer needs to show that the average daily sales at her store exceeds 7,500. So remember, what she needs to show, okay, what we're trying to prove, that is the alternative hypothesis. What we're trying to disprove is the null hypothesis, but I'll come back to that in just a moment. Question says here, historical data suggests that the purchase amount is normally distributed with a population standard deviation of 1,500. So this is going to be our sigma value. In a randomly selected sample of 24 days of sales data, the average daily sales were found to be $7,900, which is above the mean. But again, that could be a function of sampling error. So we want to run this hypothesis test here at the 10% level of significance in order to check whether or not that sample data is far enough away from this population data to argue that the sample mean is reasonable and that the actual sales are much higher than $7,500. So question up here is asking, what is the population parameter of interest? And given this information, the population parameter we're interested in here is not the daily sales at her store. It's not the number of sales days. It is the average daily sales at her store. Okay, so next question asks, given this setup here, what are the appropriate null and alternative hypotheses? And remember, the null hypotheses should always have an equal sign in some form, either a weak inequality, less than or equal to, or greater than or equal to, or a strict equality, equals, but never a strict inequality. There should always be some form of equal sign in the null hypothesis and no form of the equal sign in the alternative hypothesis. Now, what we're trying to show here, we're trying to show that the average daily sales exceed 7,500. And what we're trying to show is always the alternative hypothesis. So if we're trying to show that the sales on average are greater than 7,500, the only alternative hypothesis that correctly specifies that is here. And you're like, why not choice D? Well, choice D has an equal sign in there, which the alternative hypothesis never should. So it looks like B is a good candidate. Notice the null hypothesis is the complement of the alternative. So B is definitely the correct answer here. Okay, we're going to assume that the daily sales are very low. Then we're looking for evidence to show or to disprove that, to show that they are actually very high under the alternative. So the next question is, let's specify the decision rule here if we're using an alpha equal to 10%. Okay, so we're going to go ahead. This is an upper-tailed test since we're looking for a very large quantity of sales to disprove the null hypothesis. And in this instance, that means we're going to be looking for a table probability equal to 40%. That's going to define for us the appropriate rejection region here. So if we go ahead and we look for a table value of 40%, we're getting a number. Where is that? Let's take a look here. So it looks like if we're looking for that table value of 0.4, if you go across this row here, okay, the closest value we're dealing with is 0.3997. And notice that's much closer than 0.4015. So we're just going to use the z-value corresponding to this probability here to define that threshold. So that corresponds to a z-value of 1.28. So we can go ahead now, we can jump back to the problem, and we can denote that the appropriate critical value threshold for this test involves us being at least 1.28 standard deviations to the right of the mean in order for us to say that our sample data is far enough away to reject that null hypothesis here. So that's our critical value threshold. So that helps us specify the decision rule. If we calculate the sample mean, we convert that to a z-value, and we see that that z-value is farther to the right than 1.28 standard deviations, then we're going to have extreme enough evidence to reject the null hypothesis in favor of the alternative. Okay, moving along in the same problem here, let's go ahead and compute the test statistic now associated with a sample mean of 7,900. So again, if our sample mean x bar is 7,900 given here, we're just going to go ahead and use our z transformation, okay, plugging in x bar, mu, sigma, and n into that formula. And if we do this, we'll see the value of our test statistic here is 1.31. Okay, meaning that value of $7,900 for the average daily sales found from that sample, that is 1.31 standard deviations or standard errors to the right of the sample mean. And at this point, we're in a good spot to go ahead and think about the decision rule. Okay, so in terms of our decision rule, okay, we have our critical z-value, which was 1.28. We have our test statistic, which is 1.31. And now, again, I would always recommend drawing this diagram just so we're very clear about this. We had our rejection region defined by the z-value threshold of 1.28. Okay, our actual z-value falls to the right, meaning we are in that rejection region. So the correct decision here is to reject the null hypothesis in favor of the alternative. Now, again, this doesn't mean we've proven the alternative. It just means that the alternative is probably more viable than the null at this point. So we've invalidated the null. We've found that black swan. Okay. To conclude here, based on the data in the sample, is there statistically significant evidence that the average daily sales at her store exceeds $7,500? And the answer here is yes. There is enough evidence to conclude that the average daily sales does exceed that threshold. So that is it for this particular segment. That was running a hypothesis test for the mean of a distribution, utilizing this critical value approach when we know that population standard deviation sigma. In the next segment, we will talk about the case where you utilize the t statistic instead of the z statistic when you have to estimate that population standard deviation using the sample standard deviation S. So we'll see you shortly.